All right. So this really is going to be very quick because we've got 2 slides and an example, and that's pretty much it. And we kind of covered some of this in class already. So, um, hmm. So obviously there are 2 parts to the free energy equation. We've already talked about this. One of them is the delta H part, and the other part is the T delta S part. Okay, so the enthalpy term, the entropy term. And because the T delta S has a negative in front of it, then it kind of does, I don't know, sort of the opposite of what you might think sometimes. It all depends on the sign on your entropy. Okay, that's going to affect the sign of your delta G. I mean, it depends on the sign of your delta H too, but when we're talking about increasing the temperature, we want to think about the second term. So, and that's basically what I just said. I should read these things before I talk. But the temperature dependence comes from the entropy term. So this is kind of a useful chart, and it's in your book. I would prefer for you not to memorize this. I would prefer for you to just understand it, right? Just by looking at the equation, you can figure this out. So this is not something you need to shove into your head. You've got enough stuff there already. So if the delta H is negative, if the delta S is positive, the delta S being positive makes the negative T delta S term negative. So then the delta G is spontaneous at all temperatures at that point. Okay, so there is no temperature dependency if the delta H is negative and delta H is positive. Now let's think about that for a second. So if delta H is negative, what kind of reaction is that? That's exothermic. It's releasing heat to the surroundings, right? If delta S is positive, then what's happening? It is spontaneous, but I mean, it tends to be spontaneous, we should say. But if delta S is positive, what does that mean? Yeah, it means that the entropy, the disorder, the chaos, the number of possible microstates is increasing. The universe likes this top reaction here a lot. The universe doesn't really like anything, but so delta H is negative. So any reaction that's exothermic and increases the chaos or the entropy, that's a good reaction. That's going to be spontaneous no matter what temperature you do it at, other than 0 Kelvin, obviously, because at 0 Kelvin you have no entropy at that point. So, well, I guess even then, you have a negative delta H, so it would still be a negative delta G. But the reaction is not going to happen at 0 Kelvin. So, but at any temperature, that's going to be spontaneous. So, you know, a real typical example of this, like a combustion reaction, right? Combustion reaction is very exothermic, and it produces a lot of gas and usually breaks down whatever you're burning into smaller pieces, right? So it's going to increase the entropy quite a bit as well. Plus, you've got that great increase in temperature, so that's going to help with the entropy increase as well. So the combustion reaction tends to be spontaneous no matter what temperature you do it at. If you have a positive delta H and a negative delta S, that's non-spontaneous at any temperature. All right, so that's an endothermic reaction where things become more ordered. All right, and that just doesn't happen by itself. Okay, and that should make intuitive sense, right? You have to put energy into that because it's endothermic, and I mean, nothing gets ordered by itself, really, right? It's like your mom always used to say, that room's not going to clean itself. I don't know if your mom ever said that or not, but if she did say that, that was true. Chemically speaking, that's true. So then the problem comes if they're both negative or both positive. That's where it really comes in. Then it's temperature dependent. Okay, so it depends on what temperature it's at as to whether it will be spontaneous or not. So maybe we should just do an example of that, and maybe it'll make the most sense. So the Haber process, and again, they just talk about this process over and over and over again, but it's very important. So there's the equilibrium for that one. We're going to assume the delta H and the delta S don't change with temperature. That's a little bit of a bad assumption, but really they don't change much with temperature. So so we're probably okay there. And then we're going to predict the direction in which delta G for this reaction changes with increasing temperature. Yeah, we need some extra information here. I just realized. Which I think in the book they're assuming that you have from a previous problem. And this is, I think I labeled this right, 1990. Yeah, that's right. Okay. So, where are my values I need here? There, yeah, we calculated the value of, and 1514? Good grief. Okay, so that, now we could recalculate this. You could use the heats of formation to figure this out, okay? Actually, if you had the heat of formation of NH3, you could just multiply that number by 2, right? And that would give you the value for delta H here. We don't have to do that right now, though. So the value for delta H on this one is, I can find it, negative 92.38 kilojoules. Okay, and then the value for delta S on this one. And again, you could look up the entropy values for all of these and use the products minus reactants thing that we've done in the last couple of sections, but I think you guys have got that. So the delta S here is negative 198.3 joules per, are they giving me the units here? Just joules per Kelvin. All right, so there's my two numbers. Now the first thing you might notice about these numbers is they're not the same units, okay? And we talked about this the other day. So, well, that, okay. There's lots of things you can notice about those numbers. So predict the direction in which delta G for this reaction changes with increasing temperature. Well, which of these values are we going to look at just to make a qualitative prediction here? Yeah, we're going to look at our S value, right? Because delta G, write it down here. Delta G0 is equal to delta H minus T times delta S, right? So just thinking about it in qualitative terms, this S right here is a negative number. If I'm plugging that in down here and it's negative, the T is never negative because we're using Kelvin temperature, right? So the lowest that can go is 0. So if I multiply a negative by a negative, what's going to happen? It's going to be positive. Yeah, teachers are going to practice now. Art's just pretty good. This is on the video. I'm sorry. Yeah, I don't know what I'm doing. Okay, anyway. So when you multiply this term, please call extension 26246. Okay, well, we'll go now, I promise. All right. So negative 198.3, and you're multiplying that by a negative. That's going to give you a positive term here, right? Okay. So the bigger the temperature gets, the more positive that term gets, right? So over time, what's that going to do to your delta G? It should make it bigger, right? So the direction in which delta G for this reaction changes with increasing temperature, the delta G should increase with increasing temperature. All right? I don't know why I didn't draw an up arrow for the first increase, but I got lazy by the end. And then B, it's saying calculate the values of delta G for the reaction at 25 degrees Celsius and 500 degrees Celsius. And that's just kind of to check quantitatively to see if our qualitative prediction was actually right. So then all you have to do here is just basically plug this in twice. And be careful with your numbers because, you know, you got to watch out for your units here. So delta G equals, I'm going to change them both to kilojoules because delta G is usually in kilojoules. So negative 92.38 kilojoules minus, at 25 degrees Celsius, that's 298 K times negative 0.1983 kilojoules per Kelvin. Okay, so then we can solve that, and I'm going to cheat a little bit here rather than punching it in the calculator. Negative 33.3 kilojoules is our delta G at 25 degrees. Okay, and then the same exact thing here. Only thing that changes is our temperature number. Now again, that's not entirely true. At 500 degrees Celsius, our delta H0 and our delta S0 would be a little bit different. They just don't change very much with temperature, so we can, this is a fairly good estimate. Whoops. That's the one thing I was supposed to change. Here, let me erase it so that it looks a little bit neater. I don't have anywhere else to write it, so I have to erase it. 773 Kelvin times, this time I'll do it right, negative 0.1983. And that's going to equal 61 kilojoules. So then you can compare quantitatively, and you can say, all right, our prediction was correct. As the temperature increased, so did the delta G. So guess what happened eventually as we increased the temperature on this one? It went from being spontaneous to being non-spontaneous. So this is just another way of kind of looking at this. Let's say that we were trying to figure out the way to make the most NH3 possible. Guess what's not a good way to do that? Increasing the temperature, right? Okay, that is not a good way to make more of the NH3. Okay, and you could also see that by looking at your delta H value here, right? Delta H value is negative. That means that heat, you can think of it as being on the product side. So then thinking in terms of Le Chatelier, you add heat to this side of the equation, it's going to push it back towards the left side. Okay, so and what we're going to get into tomorrow is how delta G and K can actually be included in the same equation, because they're kind of talking about the same thing, right? So anyway, that's the temperature dependence of delta G, and that's really all there is for 19.6. This unit doesn't even get a little bit hard until the very last section. And even then, it's just a little bit hard, I think. So it's a nice break after all that acid-base stuff. So there you go. That's it for today. We'll see you tomorrow.